Hello everyone, in this video I'm going to talk about Taylor series. So in the previous video we found that to calculate Maclaurin series we need to know the value of some function and its higher derivative at x equal to 0. So now suppose instead for that function, the value of the function and all its derivatives are known at some other point x equals to a. So now we're going to create a new series which is centered or expanded around x equal to a. And that series is going to called a Taylor series. So the function can be represented by an infinite power series of the form. So fx is equal to a naught plus a1 x minus a plus a2 x minus a square plus a3 x minus a cube, and this is called Taylor series expanded around x equals to a. So what really Maclaurin series was, it's simply a special case when a equal to 0, because if you recall our Maclaurin series was a naught plus a1x plus a2x square plus a3x cube and so on. So when a equal to 0, then we get the Maclaurin series. So Maclaurin series is a special case of Taylor series. So all the conditions that we discussed for Maclaurin series gonna hold true for Taylor series as well. So it can be shown that Taylor series converges to the correct value as long as the function and all its derivative exist and there are no jumps throughout the entire interval between x equals to a and the value where the function is being evaluated. So the function can be approximated by cutting off the series after a finite number of terms. So we can find the approximation. And approximation is most accurate near x equals to a and can be made better by keeping more and more terms. And we use the same kind of procedure for finding the constants. So remember, now the series is a naught plus a1 x minus a plus a2 x minus a square plus a3x minus a cube, and we need to find the values of these constants. So the values of the constants a naught, a1, a2, a3, so they are given by the same formula that we used in Maclaurin series. So an is equal to the value of nth derivative of the function at a over n factorial. Let's do an example to find the Taylor series. So in this example, for the function fx equal to sine x, we need to find the first three non-zero terms for both Maclaurin and Taylor series expanded. So Maclaurin series, we know that it's expanded around x equal to 0. So Taylor series expanded about the point a equals to pi over 2. So then we're going to use this series to evaluate sine value, and we're going to figure out which series perform the best by comparing those values with our original value. All right, so let's do step by step. So first thing we know is that Maclaurin series is of the form sin x is equal to a naught plus a1x plus a2x square plus a3x cube plus so on, and where, so how we calculate an, so an is equal to nth derivative at 0 over n factorial. So Taylor series around pi over 2 would be given by, so some constant, so let's call b naught, b1. So instead of x we have x minus pi over 2 because we are finding around pi over 2, and then b2 x minus pi over 2 square plus b3 x minus pi over 2 cube and so on, and where, so the constants b and can be calculated by nth derivative at pi over 2 and then n factorial. In order to find the series, so let's make a table so that we can figure out all the constants first. So here we will write our suffixes n and then nth derivative of the function. So value of nth derivative at 0, and then value of nth derivative at pi by 2, which we need for Taylor series. And then we're going to write our coefficients, so an here and bn here. So for 0, so we have the original function sine x. So the value of sine x at 0, sine 0 is 0. So sine pi by 2 is 1, and an would be, so fn 0 over n factorial, so 0 over 0 factorial, which is again 0, and bn would be, so fn pi over 2, which is 1 over 1 factorial, so 1. Then for n equals to 1, we have, so derivative of sine is cosine x, and for 0, so cos 0 is 1. So again, so first derivative, the value of first derivative was 0. So 1 over 1 factorial, which is again 1. So we similarly we can look at the value of first derivative at pi over 2. So cosine of pi over 2 is 0. So b1 is 0. So for 2, so second derivative is, so derivative of cosine is negative sine x, and so sine 0, so 0. Again, our coefficient of Maclaurin series is going to be 0. And similarly, negative sine pi over 2 means negative 1. So this will become negative 1 over 2 factorial. So that is our value of B2. So this was our B naught, B1, B2. And similarly, here we have A naught, A1, A2. All right, so let's try for n equals to 3. So derivative of negative sine is negative cosine x. So cosine 0 is 1, so we get negative 1. And again, we get negative 1 over 3 factorial. So negative 1 over 3 factorial. So that is our A3. So similarly, cosine pi over 2 is 0. So we got 0 for our B3. All right, so let's do a few more. So n equal to 4. So derivative of negative cosine is positive sine, and sine 0 is 0, and this is 0. And similarly, sine pi over 2 is 1, and we get 1 over 4 factorial here. So that is our B4. So this was our A4. Similarly, when we have 5, so sine x is cosine x derivative, right? So cosine 0 is 1. So this makes 1 over 5 factorial. So that is our A5. And similarly, cosine pi over 2 is 0. So we get 0 as our B5. So we got the coefficients for Maclaurin series, which are in blue, and coefficient of Taylor series, which are in green. Thus, putting the coefficients, we get Maclaurin series for sine x is first few terms, right? So we get, so A naught is 0, so 0. A1 is x, so we get x. Then A2 is 0, A3 is negative 1 over 3 factorial x cube. So we can just simply write this as x cube over 3 factorial. Next we get plus x raised to power 5 over 5 factorial. Then we have negative x7 over 7 factorial, and so on. But since we want to write only first 3 terms, so that is what we get here. Similarly, plugging in the values for the Taylor series, so we get sine x is approximately, so b naught is 1. So b1 is 0, so b2 is negative 1 over 2 factorial. So we get this term, so negative 1 over 2 factorial x minus pi over 2 square. And again, x minus pi over 2 raised to power 4 over 4 factorial. And so we just want 3 terms. So these are our 3 terms. So we found this Maclaurin and Taylor series 3 terms for sine x for each of them. So now this part is Done. So next we need to use both series to evaluate sine of 1.658. So let's plug in this value. So using the value 1.658, here we get sine of 1.658 is equal to, so let's just replace all x's by, in place of x we're going to write 1.658 cube over 3 factorial. So 1.658 raised to power 5 over 5 factorial, and this is approximately equal to 1.0028. Similarly, we can use our Taylor series to approximate the values. So 1.658 minus pi over 2 square plus 1.658 minus pi over 2 raised to power 4 over 4 factorial. So this is approximately 0.9962. If we use calculator, so we get sine of 1.658 is approximately 0.996200169. And we notice that, so which one is better approximation? So we notice that Taylor series gives us a better approximation than the Maclaurin series. They both are pretty close, but this is closer. So what conclusions can we make from here? So we can say that the Taylor series is more suitable to evaluate sine of 1.658 because it's much more accurate than the Maclaurin series for the same number of terms. So geometrically, we do not really have to extrapolate so far with the Taylor series as we need to do with Maclaurin series. So arithmetically, we can say that the terms of Taylor series gets small much faster than the terms of Maclaurin series. So we can say that Taylor series converges more rapidly than the Maclaurin series. I hope that makes sense. So in the next video, I will discuss some properties of the series, which can help us to figure out the Taylor's or Maclaurin series for more complicated functions. Thanks for watching. See you next time.